Hello friends, in this lecture we are going to discuss transistor as an amplifier. Before discussing the application of transistor as an amplifier, let us understand something about amplifier. Amplification, it is a process of increasing the strength of a signal, or amplifier is a device which is used for increasing the amplitude of the alternating signal. It means strength of the signal. Strength means power, okay, power gain of the signal. So this is called as amplification. But in the process of amplification, one important requirement is what? Shape of the signal. Okay, shape of the signal should be unchanged and the strength must be increased without changing the shape, and nature of the signal is also unchanged. Okay, nature means if it is analog, suppose there is a signal, I am applying this AC signal to this particular amplifier, then its shape should be same when I am getting the output, which is amplified version. So strength is increased, shape same, as well as nature of the signals, are input and output signals are same. It means both are analog signals or both are alternating signals. Okay, so this is the requirement of amplifier. Now transistor as an amplifier, when we require to operate transistor as an amplifier, that time one important requirement is we have to select the configuration of transistor. Okay, we know that there are three types of configuration: CE configuration, CB configuration and CC configuration. Out of these three configurations, we know that CE configuration is suitable for amplification purpose. What is the reason? Because in CE configuration, the voltage gain, that is AV, and current gain, that is beta AC, both are moderate. That's why you are getting more power gain, because we have to increase the strength of the signal. Okay, in contradictory, if you consider CB configuration, then in CB configuration current gain is less and voltage gain is more. Okay, and in CC configuration voltage gain is less, current gain is more, so resultant product is less. That's why CE configuration is preferable as compared to your CB and CC configuration. Okay, now so it means you have to use CE configuration for amplification purpose. That's why in this circuit diagram, if you observe, this transistor is in common emitter configuration. It means emitter is common for input as well as output. Now if emitter is common for the both input and output, it means now input voltage is VBE. Why? Because emitter is common between input and output, so VBE is the input voltage and VCE is the output voltage of the transistor. Okay, and the current, input current through the transistor is IB, which is the base current, and output current is IC, which is the collector current. Okay, why? Because emitter is common, so definitely current, input current should be base current, output current should be collector current. Clear? Okay. Now this is a standard circuit diagram of amplifier using transistor, in which this particular capacitor which is used, this is capacitor. This capacitor is called as coupling capacitor. Okay, this capacitor and this capacitor are called as coupling capacitor. Why this is called as coupling capacitor? CC. Well, these are called as coupling capacitor. Why this is called as coupling capacitors? Because they couples this input signal to the base of the transistor. Okay, because we have to apply this input signal to the base, then only it amplifies it. Clear? Now this is the input signal which I am going to apply to this particular amplifier, and this input signal is actually what? Means it is a speech signal. Okay, why speech signal? Because we have to amplify this sound, we have to increase the strength of the signal. Practical purpose, we are denoting the input signal like this, but as per the convention, actually it is this symbol, but actually practically we have to use actual speech signal. We are not using this for our convenience or only for modeling purpose. Practically this is a speech signal. Clear? Okay. Now what happens when I am applying this input signal to this particular amplifier? That time there is basically we have to analyze this amplifier. Now this particular VCC is the supply voltage which is given to this amplifier. What is the purpose of it? As I am applying the input signal to this amplifier, as well as I am applying the supply voltage to this amplifier, and I am interested to increase the strength of the signal. From where that additional energy I am getting? This is an important question. So that additional energy I am getting it from the supply. So this supply will provide the additional energy to this particular input signal, and I am getting the increasing magnitude signal, or I am getting the magnified or amplified signal. So this is also the requirement of amplification. It means what? Increasing the strength of the signal without changing the shape and providing the additional energy from supply. It means controlling of shape as well as increasing the energy of the signal. It is a important function of amplification. Okay. Now when I am going to analyze this amplifier, there are basically two types of analysis are there for amplifier. First one is DC analysis, second one is AC analysis of amplifier. Now in DC analysis of amplifier, DC analysis means I am applying only DC, means I am applying only supply to this amplifier. I am not applying the input which is to be amplified. So Vi is equal to 0 and VCC is not equal to 0. This is a DC analysis. In AC analysis, if I consider, then I have to apply Vi or Vin, which is the input signal, and that VCC should be deactivated. Deactivated means I have to connect it to ground when only in AC analysis. That's why I have not shown here ground, because in only AC analysis I have to make it ground. So this is the DC analysis and AC analysis. Okay. Now listen, I am going towards now DC analysis. In DC analysis, as I already discussed, Vi is equal to 0 and VCC is not equal to 0. It means what are the modifications in the circuit diagram? This is not equal to 0 and this Vi is equal to or Vin is equal to 0. Now one important point. This Vi and Vin both are same. Vin is the actually whatever input I am trying to amplify, and Vi is the input which is going to the input of the amplifier. Actually, that way we will be discussing. Now listen here. In DC analysis, whenever I am applying the DC voltage and input is reduced to 0, that time what happens? This circuit is divided into two halves. This is the input half, this is the output side. Whenever I am analyzing the input side, that time this is a closed loop, and in this closed loop now I am going to apply the Kirchhoff's voltage law. Okay. Otherwise, suppose you have to understand in very easy manner. Suppose I am balancing the voltages in this closed loop. This is a applied voltage VBE, okay, and this is a what voltage drop across RB, and total supplied voltage is what? That particular VBB, which is a battery. So this VBB is equal to VBE plus IBRB. Clear? This is actually VBB is equal to VBE plus IBRB. So that's why this is the equation number 1. Okay. So from input side, this is the equation. From output side. From output side in the closed loop, if I consider, so this VCC, which is a supplied voltage, is equal to this VCE plus IC into RL, plus IC, current flowing to IC into RL, because current is not flowing here because it is open. So this is VCE is equal to VCC plus IC into RL. These are the two equations from DC analysis. Clear? Okay. Now I am going towards AC analysis. So in AC analysis, as I already discussed, input signal is not equal to 0, but supply voltage VCC equal to 0. AC analysis. Now there is one important question. What happens? This Vi is not equal to 0, VCC is 0, it's fine, but this input DC voltage is still present. So now it is a superimposing of your small signal input over this DC bias, which is shown in this particular diagram. So in this diagram, this horizontal red line indicates DC bias, constant voltage, and this Vi is actually applied input, speech, time varying. So there is a variations. So it is a superimposing or superposition, which means addition of two voltages. That's why this IB current is varies. Why varies? Because input is varying. So your base current also varying. So as base current varies, your collector current also varies. So as collector current varies, then your output also changes. And in this way, you can get the amplification. Okay. Now, again, we are doing some analysis. Consider input side where Vi is not equal to 0 and VCC equal to 0. This is a VBE plus Vi. Why VBE plus Vi? Because now there is a two voltages are present, that is VBE. Now another important point. Why this VBE required if we are going to apply input side? We are going to apply the input. If this VBE is not present, then this transistor will not on. And if this transistor will not on, then your amplification purpose will destroy. So you have to make it on, and to make the transistor on, you have to apply 0.7, which is a VBE for silicon, which is DC. That's why this is VBE plus input Vi. Now, as this Vi is changing, so definitely this VBE is constant, and remaining changes we have to incorporate in this equation. So this is now VBE plus IBRB, which is the voltage drop across this particular resistance, plus delta IB into bracket RB plus RI. Now from where this RI comes? Now important point, listen here. This transistor is now operating in AC domain now. Now there are different modeling of transistors. It means I have to replace this transistor with some circuit or some model. That model is shown here. This is called as AC equivalent model of transistor or BJT modeling. So whenever you are applying the input AC signal to amplifier, and in that amplifier BJT is present, then that BJT is replaced with some equivalent resistance. That resistance is called as RI. Okay, and this particular RI now plays important role, and it also gives, there is some voltage drop across it. That's why here delta IB into RI. Now why delta IB? Because your input is changing. That's why your current also changes, and this RB is already constant. That's why RB plus RI, it is a total resistance from this side. If you observe from this side, you are now observing this RB plus RI. This RI is hidden. It comes into picture only when you are applying the AC input. Okay. So now in that case, what happens? Again there is one approximation. This RB is approximately 0, or it is neglected. Why neglected? Because actually this RB is neglected means we have to keep RB small. There is one reason. Consider this diagram. Suppose I have to apply I have to amplify some input signal. Now when I apply the input signal to this amplifier, and this RB is, suppose it is more as compared to RI. Now what happens? In that case, definitely there is a problem. Why? Because listen here. This Vi is equal to Ri upon Rb plus Ri into Vin. From where this equation comes? Voltage divider rule. So voltage across is Ri upon Rb plus Ri into Vin equal to Vi. Clear? Now if this Rb is very greater than Ri, then what happens? In this case, this particular Vi is too much less than Vin. It means if you are applying 20 millivolt, which is a signal which is to be amplified is 20 millivolt, and your amplifier is getting suppose 5 millivolt, then what is the use? Then that 15 millivolt has been wasted. So that is not desirable for us. That's why in the amplifier analysis, this Rb should be very much less than Ri. And if you are keeping Rb is less than Ri, it means this sum is Ri. It means Ri cancel. So Vi is approximately equal to Vin. Approximately. That's why we have to assume RB equal to approximately equal to 0. So when this RB is equal to 0, that time what happens now? Now important point, RB 0, so definitely this term will cancel out, again this term will cancel out. So what I am getting now, Vi is equal to delta IB into Ri. So if you are observing now, Vi is equal to delta IB into Ri, and from this you are getting Ri is equal to Vi upon delta IB. So this is the expression for AC equivalent resistance. Now if you observe in this formula, you are getting delta IB because as name suggests, it is a AC equivalent. So as you are applying the input which is time varying or changing with time, definitely your current also changes. That's why there is delta IB. Okay, so now important point, AC current gain of transistor, as we discussed DC current gain, which is a what? Delta IC by delta IC upon IB in case of DC, that is beta DC. Here it is AC, so delta IC upon delta IB. Why only delta IC upon delta IB? Because our transistor is in common emitter configuration. Okay, now as changes in IB causes changes in IC. Okay, now due to that IC changes, so output voltage also changes because we are getting the output across load, which is a collector resistance. Now VCC is equal to VCE plus ICRL, from where, as I discussed this equation in the DC analysis. So I am taking the equation from DC analysis, VCC is equal to VCE plus ICRL. So delta VCC, delta VCE plus delta ICRL. Now what is the necessary to take this delta VCC? As I am applying AC signal, that signal is changing, so definitely I have to show this equation also which is changing. So but this VCC is constant, that's why this is 0. So delta VCC 0. So delta VCC 0. So now if I substitute here, delta VC is minus delta IC into RL. Now again we proved AC current gain beta AC is delta IC by delta IB. So I am substituting for delta IC here. So delta VC is minus equal to minus beta IC delta IB into RL. Now, but this is the expression for delta VC. But delta VC is equal to delta VO. Why? Because this is only the output voltage. That's why delta VO is equal to minus beta IC delta IB into RL. This is the expression for change in output voltage. Why change in output voltage? Because there is a change in input current, and transistor is a current control device. So as the input current is changing, correspondingly output current changes and voltage across it also changes, because as per Ohm's law, V is equal to IR. Okay, now input changes in the input, delta Vi is delta IB into Ri, because as input current changes, input voltage changes. Why only I am taking the Ri? Because AC equivalent resistance, RB has been neglected. Now we are ready with what? Change in output and change in input. Now we are going to calculate what? AC current gain, that is change in a ratio of change in output to change in input, which is actually minus beta AC delta IB RL upon delta IB Ri. So this delta IB cancel. We are getting, now I am defining one new term, AV, voltage gain AV, which is equal to minus beta AC RL upon Ri. So this is the important equation that we have to remember. Voltage gain of transistor in common emitter configuration is minus beta AC RL upon Ri. RL means load resistance, Ri means AC equivalent resistance. Okay, yes. Now important point, this minus sign indicates the output voltage and input voltage are not in phase. What is meant by not in phase? Listen here now. Suppose this is a input voltage. Listen here. This is a input voltage and this is a output voltage. Again I am drawing another waveform for output voltage, which is like this. These two are different. First one is what? It is in phase because they are going towards 0 at same time. They are reaching to maximum side at same time. They are reaching to negative side also same time. First and third, if you observe, there is a difference. So this is called as out of phase because these waveforms are not starting at same time. So in common emitter configuration, output voltage is out of phase by input voltage. And what is the phase difference? Exactly 180 degree, pi radians. Clear? This is an important point. Minus sign is a catch here. Now we have to calculate power gain. Power gain, because in transistor amplifier more important is strength of the signal. So strength means power gain. So power gain is equal to voltage gain into current gain, because as we know that power is voltage into current. So gain, power gain also voltage gain into current gain. That's why power gain AP is equal to AV into beta AC, where AV is the voltage gain and beta AC is the current gain. Now as I calculated the voltage gain minus beta AC into RL upon RI, I am taking the magnitude, that is modulus. So it is beta AC into beta AC RL upon RI. So after simplifying it, finally you are getting power gain AP is beta AC square RL upon RI. This is the important formula in transistor amplifier in common emitter. Power gain AP is beta square RL upon RI. Okay, so I am now recalling three formulas. Voltage gain is what? Minus beta AC RL upon RI. Current gain is what? Beta AC. And power gain is what? Beta square RL upon RI. So this beta, as beta is more for transistor, range is what? From 50 to 200. So as beta is more, definitely your power gain is also more. So in this way you can increase the power content, or you can increase the strength of the signal. And that's why these common emitter amplifiers are so popular, because they provide more power gain. And what is the basic important cause for the increment in power gain? This beta value, that is what? Common emitter current gain. And that's why these common emitter amplifiers are preferred in public address system to increase the strength of the signal. Okay, so in this lecture we discuss common emitter amplifier using transistor. I discuss it. First I discuss the definition of amplification. Later on, what are the important components present in the circuit, their significance. Afterwards, types of amplifier analysis, what is DC analysis, AC analysis. Later on, some expression for DC analysis. In AC analysis, I discuss modeling of BJT, how to model the BJT, what is meant by modeling. Then AC equivalent resistance means what, and then next I discuss AC equivalent resistance formula. Afterwards I calculated the change in output, then I calculated change in input, I take ratio, and finally I calculated the voltage gain. And from voltage gain and current gain, finally I derived the formula for power gain, which is important for the amplification purpose. So in this way we have completed transistor as an amplifier, which is an important topic from exam point of view in all respect. Thank you.